NASA's planetary science and planetary defense efforts. So let's see, I guess I got a consent to being recorded here, so I've done that. And so with that, let's see, let me bring up some slides here, talk to you about the, let's see, Rick telling me that you disabled my screen sharing. Okay, looks like I can do it now. Let's see here. Well, now it's not giving me my window. Is that showing PowerPoint yet?
Nope.
No.
Okay, now let me try it. Sometimes it takes a while to get all the right combination here. How about now?
Yeah.
Okay. Okay, good. Let me try this, Rick, see if something got cured. Rick and I tried to test a little earlier, and when I went to presentation mode, it didn't switch, but let me try a second and see if it will switch.
We have to get the recording, the sign of recording, get that out though.
Is that still showing on my screen?
I don't know, but it's showing on mine.
Lindley, if you want, you could just make it a little bit bigger on your bar down at the lower right, and that might do it instead of going to presenter mode.
Yeah, no, we had a backup, but I think whoever is seeing the consent to recording, it's on their screen, not on mine.
Okay.
Okay, so it's not jumping to presentation mode, huh? So I had the same problem. Okay. Well, I'll show them this way then, and I'll have to remember to activate some of the animations as I go along. Okay, well, as Rick said, I'm the NASA's Planetary Defense Officer. I run the Planetary Defense Program for NASA, and we have what we call the Planetary Defense Coordination Office at NASA, which was set up about 5 years ago. Let's see here, let's go this way, okay. And so we've had that office set up for about 5 years, but NASA's been in this business for a little over 2 decades now, and trying to find the near-Earth asteroid object population. But recent years, our activity has expanded, and so this office was set up to manage the planetary defense activities at NASA, but also coordinate across the U.S. government in our interagency and with international efforts to study and plan a possible response to an asteroid impact hazard if it were detected. So we lead both national and international efforts to detect any potential impact, be able to appraise what the effects might be based upon what we can determine about the object before impact, to advise what might happen. Is it small enough that it might burn up in the atmosphere and we don't have to worry about it, or is it large enough that significant damage could result from the impact? And then given enough time, which is really what our program is all about, is finding these things as early as we can to increase the amount of time we might have to respond, have efforts to mitigate the impact effects, possibly by deflecting the asteroid while it's still out in space. I know several of you on here know what near-Earth objects are, but just to be clear what we're talking about, asteroids and comets that come into the inner solar system, and within about 1.3 astronomical units of the sun. It's really, the name near-Earth objects is a bit of a misnomer, in that a lot of times these objects are nowhere near the Earth. They're someplace else, other side of the sun, but they have the potential to come near Earth because of their orbital paths. And we're particularly looking for those that are potentially hazardous to the Earth, those that come in within this a ring around the Earth's orbit of about 5 million miles and could actually represent a true impact hazard over time. As an example of asteroid that's been in the news quite a bit lately, Bennu, which was the destination of NASA's OSIRIS-REx asteroid sample return mission, is a potentially hazardous asteroid and has not insignificant potential of impact in the Earth, possibly in the second half of the next century, in 2185 or so. Our planetary defense program, we have a number of activities that go on in these various sectors. Of course, this is what we call our strategy document, and you kind of read it like a clock. Up in the upper right-hand corner, our most highest priority activities are just to search, detect, and track these objects. David is involved in a lot of that activity. Then be able to characterize specific asteroids that we find, to learn more about their character, and in particular, if it's something that is a hazard to Earth, its size, composition, so we know something about what the effects might be were it to impact the Earth. A good deal of our effort is involved in planning and coordination, as I mentioned, across the U.S. interagency and with our international colleagues around the world. And then the area that everybody likes to talk about is mitigation, particularly in-space mitigation, doing something to prevent the impact. Impact of an asteroid is one of the few natural disasters that we could prevent from happening if we find out far enough ahead of time about them. And of course, we need to be able to assess our success across all these areas. And are we doing what needs to be done, and what can we do to improve it? Our guidance comes from a national near-Earth object preparedness strategy and action plan that was under development for about 3 years prior to it being signed out almost 3 years ago now. How time flies, but you can find that document there at that link. And what it is it's not the grand plan or what everything is going to kick into action when we find a impactor, but it is about improving our capabilities to be able to respond to a potential impact hazard. So it's a 10-year action plan to improve our capabilities, first of all, to detect, characterize, and track near-Earth objects. There is a lot of modeling, orbit modeling, effects modeling, atmospheric penetration modeling that goes on to determine all these things, predict when the impact might occur and what might happen, to be able to inform our leadership about it. And so across various agencies, this information needs to be integrated. Then development of technologies for near-Earth object deflection or disruption, if it is in a shorter period of time, to try to minimize the effects of an impact, working internationally with other nation space agencies and other offices to bring the best capability we can in the world to such a event. It's not going to be just the U.S. An asteroid impact will be by its nature an international issue to be dealt with should one be discovered. And then within the U.S. government, establishing and improving our emergency protocols and action plans to be able to deal with such a natural disaster. So finding NEOs is, as my program manager likes to say, it's like looking for a needle in a haystack, because at first glance, this is an image, Catalina Sky Survey, a discovery of a near-Earth object, and because of the animation isn't working, you can't see that asteroid crossing the field of view there. But it looks just like another star in most of our surveys until you take a series of images and see it move across the starscape. So the Near-Earth Object Observation Plan was established back in 1998, as I mentioned, but our most recent guidance comes from the National Authorization Act 2005, which laid out the goal for NASA to find and catalog 90% of near-Earth objects greater than 140 meters in size within 15 years, and that was last year, and we did not reach this goal. And so we have some work to do with what we call the George E. Brown Near-Earth Object Survey Act, named after a previous chair of the House Science Committee. So NASA's search effort today involves mostly ground-based telescopes, but we are working on more space-based capability. Catalina Sky Survey, run by the University of Arizona, and the Pan-STARRS telescopes, two telescopes run by the University of Hawaii, as you see here in a minute, are finding the majority of near-Earth asteroids these days. But a good number are also found by the Atlas system, which is right now a couple of sites in Hawaii that are able to scan the sky quicker each night than the bigger telescopes of the University of Arizona and Pan-STARRS, and could pick up a 100-meter sized asteroid a couple of weeks if it were on a impact trajectory, to at least be able to give warning for, say, evacuation of an area. We're also working with the Department of Defense and the U.S. Space Force. They are deploying a new space surveillance telescope into Western Australia, and we have worked with MIT Lincoln Lab to develop that telescope so that while it's doing its prime mission of space domain awareness for the U.S. Space Force, it can also detect and track asteroids moving across there in the background of stars of those images. That system is in testing now at Australia and will go into operations here in about another year. We also get data from a number of other telescopes around the country, for instance, Caltech's ZTF facility. And we have one space-based survey capability right now. It's a repurposed astrophysics mission called the Wide Area Infrared Survey Explorer. And after it finished its one-year mission for that, developing an infrared survey of the sky, with all the images that it's able to take, it makes a good asteroid hunter, as well as that infrared data can be used to characterize the size of these objects with those observations as well. So our process, discover these objects, the detections come in from the survey observatories, all go to the international sanctioned Minor Planet Center for observatories around the world know to send their astrometric observations to the Minor Planet Center, where the identification that it is a new object and not something that's already in the catalog, and the designation and an initial orbit computation is done. And then astronomers worldwide provide observations over the course of the next few days to weeks, so that we are able to secure that orbit and be able to predict it out into the future. Then all the data on near-Earth objects, Minor Planet Center does small bodies throughout the solar system, but for near-Earth objects, our Center for Near-Earth Object Studies out of JPL then takes them the observations and does a high precision orbit determination for both short-term to determine whether there's any immediate hazard from the near-Earth object, and more long-term, predicting these orbits out as much as 100 to 200 years in the future to determine whether they represent any hazard. And then if there is potential for impact, determining when the time, location of that impact might occur, and then alert messages are sent to us at NASA from CNEOs. As I said, we also work with the international community. We have worked with the United Nations Committee on Peaceful Uses of Outer Space. NEO response, international response, has been on their agenda for about 20 years now. And under negotiations that occurred at the committee, it was agreed to set up two entities. Now, these are not United Nations entities. These are coalitions of the willing, so to speak, of capabilities of space agencies and observatories, space institutes around the world, to first of all have an international asteroid warning network where observers, orbital analysts, and modelers provide their efforts to determine potential hazards and impact time and location. That effort is organized by NASA. And then we have the Space Missions Planning and Advisory Group, the so-called same page for all of the, it's a forum for the national space agencies to collaborate and cooperate on capabilities that could be used to deflect an asteroid in space should we need to. A number of signatories to the International Asteroid Warning Network of observatories and space agencies around the world. You see contributions by China and Russia and almost every major space agency that there is in efforts to find and track near-Earth asteroids. And the network reports its activities out to the Committee on Peaceful Uses of Outer Space on an annual basis. And I have the joy of going to Vienna, Austria about once a year when there's not a pandemic anyway, and to the committee meeting, subcommittee on technical, scientific and technical subcommittee to report out our activities. So where are we in finding near-Earth asteroids? Well, as we said, we've got a few more than 17,000 now. In fact, a couple of months ago, we broke through 25,000 now asteroids of all sizes in the catalog. Almost 26,000 now, as you see on the right side there, of all sizes. A little under 10,000 of them now, though, are greater than 140 meters and so in size, and a little less than 900 are greater than a kilometer in size. About 10% of them or so are in potentially hazardous objects, come within 5 million miles of the Earth's orbit. And so the orange area that you see in this curve are the 140 meters and larger. And then down there at the bottom, you see the red curve is the 1 kilometer and larger, and you see that has flattened out now. In fact, in the last few years, we've only found per year 2 or 3 1 kilometer and larger asteroids, and in fact, this year we haven't found any yet, with 5 months already passed almost. All sizes by survey here shows you that Catalina and Pan-STARRS are 2 big discovery surveys, and then with contributions from these other projects that I talked about. Last year set a new record, almost 3,000 near-Earth asteroids of all sizes found. And this year so far, we're pretty much on track to get to about that number again, if things hang together and the weather's not too bad in Southwest or Hawaii. But the 140 meters and larger sizes of the so-called George E. Brown survey goal, we're only of all of those, only about a fourth of them are 140 meters and larger, and we've kind of leveled out here at about 500 objects a year. And in fact, this year, if the pace doesn't pick up a little bit, it'll be a challenge to get to that 500 number. So that just tells us that our current capabilities are somewhat limited in being able to find these objects. We have to wait for them to come to us, come within range of our current capabilities. And so this is another way of looking at the problem here. This red curve is the population model of objects of these sizes down in these bins, size bins down here, the number of objects that the model shows to be existing. And so we've done pretty well. We believe we found all the near-Earth asteroids that are, 5 or 6 kilometers in size now. A few numbers still to be found in a few kilometers in size, although this may be more small number statistics than anything here on this dip, because the numbers down in here are in the tens of objects. Whereas if you get down into the 100-meter or so class, we're talking thousands and tens of thousands of objects as you get down to about 100 meters or so in size. And so it's in this area now that the challenge exists to find the rest of these objects. And so as a pie chart, if the whole pie represents this population of 140 meters, we believe that population to be about 25,000. And to date, as of the end of last year anyway, it still remained about 60% of this population still to be found. There are about a little over 15,000 or so. And so at the current rate of 500 or so a year, you do the math, it'll take us about another 30 years to complete this survey that we had been tasked to do by 2020. So we've got to improve our capability here, and our mission that we have under development now to do that, a space-based IR telescope specifically designed to detect and track near-Earth asteroids, and be able to directly determine their sizes from the IR signatures. We have now ready to start preliminary design. In fact, on Tuesday of this next week, we have what we call our key decision point B review for this project. We think they're in good shape to be able to enter the phase B preliminary design phase, which means they're about, would be about 4.5 years from launch with the development, assuming we can then, this gives us the authorization to then go get it into the program funding for our program office. And one of the reasons we want to look for them in the IR is that if you have two similar sized asteroids, one that's quite reflective or bright, and the other one has, many of them are quite dark, low albedo, as we say. If you see these in the visible, they can look quite different. In fact, at a distance, the dark one pretty much disappears against the background of the sky. But if you look in the infrared, the re-radiation of the solar heat is proportional to the size of the asteroid and not its reflectivity. They appear with the same signature of the same size object in the IR. So that's why it's advantageous to look into the infrared. But we've got to go to space to be able to do that, because the Earth's atmosphere absorbed a lot of the IR signature. So the NEOWISE spacecraft, as I said, that we currently have, its field of regard is just this very narrow 1 degree band of the sky, perpendicular to the Earth-Sun line, whereas the NEO Surveyor, which we intend to station at the Earth-Sun L1 point, is able to survey this broad area of near-Earth space, both in front of the Earth's orbit and behind the Earth in its orbit. It spends 2 weeks looking this direction, and then flips over and spends 2 weeks looking in this direction, and then back and forth through time. And so it'll be capable of pretty much cleaning up the near-Earth asteroid population within 5 years for about 2/3 of it, and a 10-year operation would complete over 90% of and achieve the goal that we're looking for. So most people don't realize that we have close approaches of asteroids to the Earth all the time. In fact, in 2020, there were 107 asteroids of all sizes that came closer than the Moon. Now, thankfully, most of these were pretty small, and were they to impact, they would have been disintegrated in Earth's atmosphere. But a few of them are more than 20 meters in size, which was the size of the Chelyabinsk, about the size of the Chelyabinsk asteroid that came in over Russia back in February of 2013, and air blast from that did some significant damage and injured about 1,600 folks. And then one was almost as large as 200 meters in size, which is not something we would want to get hit by. 7 of these asteroids approached within the distance of the geosynchronous satellites. You can go onto this website here of our Center for NEO Studies and see all the close approaches that are occurring over time. It's all published on our website. So last year, we set a record for a known close approach, closest known asteroid to approach Earth back in August of 2020, but then immediately 2-3 months later, that record was broken with about 10-meter size asteroid that that skimmed along about 375 kilometers above Earth's surface, which is just about at the altitude that the International Space Station flies. So that got a few people's attention. But we have impacts of asteroids all the time too. Luckily, most of them very small. But over the last, 30 years now, US government sensors have detected 866 impacts of asteroids at least a meter or larger in size. And on this scale, anything that's in the orange or above is energy release as it hits the Earth's atmosphere is equal to or greater than the Hiroshima device atomic bomb. And so there are about 15 events that have occurred over time here that were larger than the Hiroshima blast in Earth's atmosphere. Chelyabinsk, as I mentioned back here in 2013, was about 440 kiloton energy release. And then back in December of 2018, Bering Sea, there was another event, about a 10-meter sized asteroid released about 50 kilotons of energy. And sometimes we find these things before they impact. Here's an example of how the system is supposed to work. Luckily, in this time, a very small object discovered by Catalina Sky Survey. We knew immediately because of its size that it wasn't a real risk and would disintegrate in Earth's atmosphere, but this allows us to exercise our system a little bit. Initially detected 8 hours prior to impact, and observations then also came in from our ATLAS system, so that the Center for Near Earth Objects could do an impact prediction. The initial track from Catalina Sky Survey had this impact corridor stretching across the Indian Ocean and into South Africa. But with those few additional observations from ATLAS, are able to narrow that down into area of South Africa where the impact would occur. And so then at the appointed time of detected predicted impact, sure enough, this is footage from a farmer's security cameras. This bolide came in and detonated over Botswana. Now, this camera was actually in South Africa, several hundreds of kilometers away. And so this is not the bolide hitting the surface, but actually detonating here in the Earth's atmosphere, but it's over the horizon. So quite an event for an object even that small in size. And so reported both by US government sensors and also by comprehensive test ban treaty monitoring stations that monitor for nuclear tests and violations of the test ban treaty, are able to detect these detonations in Earth's atmosphere in the infrasound. So data is collected from all kinds of sources. And we use that data then to, when it occurs over land, to send out meteorite hunters. This is a free sample return of the very closest near-Earth asteroids. And we like to get this into the labs as rapidly as possible. So for this particular event, a team was sent out to Game Reserve in Botswana. They're pointing at their first find, and it's this little meteorite over here that you see. All in all, about 24 meteorites were recovered, totaling about 215 grams of material from this impact. This data samples go into the labs and reveal more about the composition of the near-Earth asteroids. We also send teams about every summer in the Antarctic, of course, wintertime here in the U.S., but send teams into the Antarctic to collect meteorites off of the ice sheets where they stand out from the snow. That all goes information, as I said, a lot of the modeling is done for asteroid threat assessment project at Ames to take the characteristics of asteroids, model it as it enters the Earth's atmosphere, atmospheric entry modeling to determine whether composition and size would cause it to break up or could it survive all the way to the surface, and what those effects could be, both blast and thermal, at the surface, so that we can make some prediction of what the damage could be and advise leadership of what the risk for a particular event might be. We also do exercises with the Federal Emergency Response Management Agency. This particular exercise was one over done in Southern California, where we simulated having found an asteroid about 4 years early and tracking and predicting its impact point about 5 months prior to impact with just optical only tracking. 100-meter object could impact in a swath across Southern California. And then with the effects modeling that we do, such an impact, 100-meter or so object, and 30 days out, we could narrow down the impact point to within a few kilometers of where it would impact, so that the emergency response community knows what they may be facing as far as getting populations out of harm's way for an object of this size. It's quite a large area, utter devastation out to 10 miles, very heavy damage out to 20 miles radius, and a total of 2,500 square miles could be affected by just an object of 100 meters or so in size. Characterizing NEOs, this is a part of this business that Humberto is closely involved with. We run NASA's infrared telescope facility out at Mauna Kea in Hawaii. It's used for a lot of planetary astronomy, but also set up for rapid response for characterization of near-Earth asteroids should one be found. And then also with planetary radars, there were 2 capable planetary radars, NASA's own Goldstone planetary radar in Southern California, and then Arecibo. But I think you all have heard what occurred with Arecibo last December, and lost that capability. I don't know if you had, I think you were expecting trying to get a presentation from somebody from Arecibo. But the planetary radar capability there at Arecibo was funded by our program. And we're always, the radar capability, if the signal to noise is high enough, they're close enough in range, we can do radar imaging of the objects and get pretty good idea of the shape and size of the objects, and even if they are binary or even triple bodies. One of these was animated, but okay. So the last few minutes I have here left, let's talk about mitigation techniques. It's been quite a bit of study of this, but the National Academies about 10 years ago did a study showing that the technology that we currently have, we've got about 3 viable techniques that could be used to deflect an asteroid from an impact trajectory. Now, these are all based upon just changing the orbit velocity of the objects by less than a percent. If we can shave just a centimeter per second off the velocity of the asteroid several years in advance, then the orbital dynamics just take care of it from there and make what would have been a predicted hit be a complete mess. Most advanced technology, kinetic deflection. This technology has been demonstrated for other purposes. Another idea is a gravity tractor, where you just have a spacecraft, possibly its mass enhanced by going down and collecting a boulder off the surface, and then station keeping beside the asteroid, and slowly over time, nature's tug gravity will modify the orbit of the asteroid, and we can actually control what the new orbit is that we can tug it into with this technique by tugging a little while, assessing what the new orbit is, and if we need to move it more, we just tug some more. And then there's the Hollywood technique we like to talk about, but we wouldn't try to blow the asteroid up because then you just have a bunch of shrapnel headed at you. But deflection by explosive, we detonate a standoff device which irradiates the shell of the surface, blows off a surface layer of the material, and of course there's then an opposite reaction in the trajectory of the asteroid. And then finally, the kinetic impactor, and we are actually have a mission that's almost ready to go to demonstrate kinetic impact deflection technique. We're going to do it on the moon of Didymos, change the orbital period of this moon with this kinetic impactor demonstration. It's in final integration and testing now at the Applied Physics Lab, and although it was originally scheduled, launch window was scheduled to open this July, because of delays due to COVID in some cases of some of the components, we've slipped to its secondary launch window in November 24th of this fall, but it will still impact the Didymos moon, which is now called Dimorphos, into September of 2022, and change the orbital period of the moon, which we will then observe from Earth-based observatories. It's an eclipsing binary, and so we can observe the light curve and see how much the period of the light curve has changed due to our effects on the moon. So look for that launch here in November, and follow us for the next year as we then impact the asteroid, and then take observations from ground-based observatories for the next several weeks to months into the rest of 2022. As I said, DART is finishing up its integration and testing, and we'll be ready to ship to it'll launch from Vandenberg Air Force Base. I should say Space Force Base now, just recently renamed as a Space Force Base in late November of this year. And with that, I'll take any questions you might have.
Wasn't there another simulation that I just read about recently that involved Europe of an asteroid?
Yes, you probably read about the end of April. We have every 2 years we have a planetary defense conference, International Planetary Defense Conference, and as part of those conferences, we have a exercise, impact emergency exercise, where we simulate potential impact of an object. In some cases, several years in advance, so our spacecraft designers can work on it. But for this particular one, we made it what we call a short warning, only 6 months in advance. There's not much we can do about it in space. And this was really designed to get this time to get the emergency response managers to really think about what would we do in such a situation.
And to build another radar system now that Arecibo's down, in addition to the one that we have remaining?
I think your question was, how do we replace Arecibo? In fact, Arecibo is a National Science Foundation facility. And in fact, they are having a workshop here in June to talk about concepts, discuss potential concepts and capabilities and new technology that might be used to replace the Arecibo capability.
I have a question.
You're
Do you
not
happen to
allowed,
know?
Roberto. No, go ahead.
Yeah, okay. By the way, you are a reference on my security clearance, so I'm in trouble.
Boy, are you in trouble.
Anyway, do you happen to know the type of meteorite that Botswana was? It looked dark, so it might be one of the primitive meteorites.
I think it's a head.
Okay.
From Vesta.
Wow.
If I remember correctly, but there's a paper out. I can send you the reference to it.
Okay, thank you.
Lindley, you mentioned a number of surveys that have sort of
Hi, Barbara.
gotten into the business of LSST before LSST or the Vera Rubin Observatory will be able to. But will Vera Rubin Observatory make a significant difference in this game?
Well, we think that they should be able to provide a number of detections, both of previously unknown near-Earth asteroids, but also provide a lot of follow-up observations that are needed to continue to track the orbits. Their cadence is not really optimized for this kind of work. Their real mission in life is dark energy. They're trying to cover all the sky about every 3 days or so, and so that they can't spend too much time in one part of the sky to do that. And we really need at least 3 observations a night, if not 4 or 5, to make sure we catch the object to be able to establish a good orbit on it. Because when you come back, say a week later, it may be gone, or it may have dropped. Signature may have dropped below the detection limit again. So anyway, but we are really hoping that LSST can provide a lot of observations to the Minor Planet Center, just as the other surveys do.
I assume that the cadences can be changed if some of the primary targets get achieved. I don't really know what they are or how.
Yeah. Well, it has a 10-year program that it's being set on for that cadence. We've had discussions about this, believe me, with NSF and the LSST team. They think they can contribute quite a bit with the two images about 30 seconds apart each night. We'll see how it goes.
Okay, thanks.
You showed the field of regard for NEOSM and mentioned that it would be spending a couple of weeks looking ahead of the Earth's orbit and then spend a couple of weeks looking behind the Earth's orbit. But that's a two-dimensional diagram. So I was wondering about out of the plane of the diagram, you know, above the Earth and below the Earth, is it just going to be kind of cycling like a torus, or is it going to preferentially hit the ecliptic regions at the expense of the out of the ecliptic?
Well, first of all, it'll go about 20 degrees above and below the ecliptic. We do have to keep the Earth and the Moon out of the field of view because they're too bright. You know, 45, yeah, I think it's 45 solar elongation to 125 on both sides, and then plus or minus 20 degrees in the ecliptic.
So when you get to your 90%, are there plans to extend the range that you're looking after that?
Well, we're operating for as long as we can. I mean, range is, you know, really determined by the sensitivity of the detectors. But more than that, we'll probably be looking for what is the next generation survey detector system. Because, you know, we know objects smaller than 100 meters in size, if it were to hit the wrong place, could do a lot of damage.
Lindy, I have a quick question. My name's David. I work with Gary Hug out at the Farpoint Observatory.
Yeah, I meant to mention you guys when I talked about the follow-up capabilities that, you know, the team out there is one of these sort of semi-pro, I would call them, not amateur astronomers, but semi-pro. Go ahead.
So my question is, as the new telescopes are put into play either out in space or ground-based, do you still see these follow-ups by observatories such as Farpoint having a role?
Well, I think they will always have a role for what they're able to detect. We're looking for those objects that can come near the Earth, and so at times they come near the Earth and are in the detectability limits of whatever the capability is. We want the observations taken on them and sent to the Minor Planet Center.
Okay, thank you.
Lindley, if I may, another question. The European Space Agency is planning a mission they call the Comet Interceptor, where they're going to park a spacecraft, and then if a good comet comes along, they're going to go catch up with it. Would there be a similar concept that could help your mission?
Well, I hope a comet comes along that is within the capabilities of their mission. You know, it is an asteroid impact of significance is a really rare event. And the chances of it happening in our lifetime, something that we really want to send a deflection mission to is also extremely rare. And so the operational cost of trying to keep something up and running, you know, for whatever period of time that might be, it could, you know, granted, you know, it could be in just a few years, but more likely it will be many decades before we would need such a capability. And by then we should have even better technology to be able to take care of it. So I don't really see that as a practical solution, stationing something in space, just waiting, you know, for the wrong rock to come along.
Thanks.
Okay, well,
Go ahead, Lindley.
I enjoyed being with you here tonight, and if any other questions come up, you can shoot me an email.
Yep, I don't see anything in the chat, so I think everybody that had one popped in, but certainly if anything comes up, I can forward any questions to you, or give your email address to anyone that wants to ask the question.
Yeah, sure.
Geraldine, did you have your? Oh, you were clapping. I'm sorry. I thought you were. You had your hand up. All right. Well, thank you very much, Lindley. That was very interesting presentation. I appreciate you coming on and joining us, and I will get this recording cleaned up so that everybody has the chance to look at it or forward it on to anyone that wasn't able to make the meeting. So thank you very much, Lindley.
Sure, yeah, and in there you'll see web links to all of our information on Planetary Defense Program, and also the Center for Near Earth Object Studies, where all the data is publicly available, and you can keep track of our progress through the years.
Great. All right. Well, just a quick note before we sign out. For those of you that I'm going to go ahead and send out that invite to the club members for tomorrow. I know there was a couple of people that weren't able to attend, but if those of you that can't attend tomorrow want to just send me an email with your thoughts about the subjects that we were talking about discussing, then just shoot that over to me so we make sure we get your input. And this is our last last club meeting for the spring, so we'll be starting back up this fall, and hopefully we'll be able to see everybody again instead of just having meetings on Zoom. So Lindley, thank you very much. For all our other speakers, Dave and Umberto and everybody else that joined us this spring, thank you all very much. It's been a great spring of meetings. So, all right, we'll see everybody in the fall or earlier. Thank you.
Take care.
All right, thanks.
Bye, everyone.